Alright, sorry for the delay. Were you guys able to hear me now?
Yes, sir, you're audible.
Okay. So it seems there is a network issue. So maybe I will not switch on my camera today. Uh, if the, let's say, if the internet network issue improves, maybe I will switch on my camera. So uh, without further delay, let me start the session today. I'm just checking my recording. Okay. So, what we are going to do today is we are going to solve two problems. One is going to be on pumps, and the other is going to be related to the liquid monopropellant. Okay, and after that, in the last class, we had a lot of discussions and questions about the this solid propellant regression regarding a certain problem in the assignment. We will also look into it. I will this time probably I will be able to explain you guys better. Um so that is the agenda for today. Do you guys have any questions before we start? We will be so the two questions will be very quick. We will complete it and also we can take questions. So if there are any quick questions you wanted to ask me now, maybe you can do. All right. So uh, I don't think there is any problem from about audio, I guess. So you can just give a thumbs up or you can say yes. All right. Thanks, Akhilesh. So we'll get started for today. Um, the first question is going to be about pump. So we all know that there is going to be, if we are dealing with liquid propulsion system, liquid propulsion, liquid rocket engines, there's going to be a tank and there's going to be a pump which is going to provide the propellant at a certain pressure. So we now today in these questions we are going to focus only on the pump. Okay, so the pump here is operating at a speed of 30,000 rpm and a liquid hydrogen of density 70 kg per meter cube. Okay, and it is at a temperature of 18 Kelvin. So if hydrogen is liquid, then it is going to be at low temperature. So here it is 18 Kelvin, and it also has a vapor pressure of 0.006 megapascal. Okay, and is pumped at a flow rate of 10 kgs per second. So these are the some parameters given for liquid hydrogen pump. Okay, the pressure at the inlet of the pump is this much, and the exit is 10 megapascal. It is found necessary to modify the turbo pump for a flow rate of 12 kgs per second. Okay, so there is already a pump which has been designed for 10 kg per second with all these parameters. Now they are trying to modify it for a flow rate of 12 kg per second because of various reasons, like they may need to increase the pressure, uh, right? They may need to increase the thrust. So increasing flow rate means increasing thrust, uh, uh, which is required for a particular mission. So without changing the dimensions of the pump and supply and exit pressure, so they don't want to change the dimensions of the pump. Basically they don't want to change the whole rocket system. So without changing that, I want to modify the flow rate. If I want to modify the flow rate, we are asked to calculate certain parameters. What is the specific speed of this pump? What is the speed of operation for an increased flow rate from 10 kg per second to 12 kg per second, and what is the net positive suction head? So these are the three parameters they are asking us. So let's see, how do we solve this problem? Let me just quickly write the given so that it's very clear, so that uh, maybe everyone can understand the question better. So there is a liquid hydrogen pump which is running at 30,000 rpm. Density is 70 kg per meter cube. This is density of liquid hydrogen, and temperature is also given. This is the temperature at which it is stored, 18 Kelvin. And then there is a vapor pressure given, which is 0.006 megapascals. flow rate, it is in kg per second, so m dot of hydrogen is 10 kgs per second. Pressure inlet to the pump and exit, so P in is 0.05 megapascals and P out is 10 megapascals. Now we need to modify, so let's say, so the modified m dot dash, let's say, is 12 kg per second. Okay, so is there any question, is there any doubts with regards to the question? So how do we, so this is, let's say, a pump, 0.05 megapascals and 10 megapascals, and then m dot is 10 kg per second. Okay, so we need to find out specific speed, that is the first one. Specific speed, we call it ns, right? So this is pretty straightforward. We have already equation, specific speed equation. So how does that look? Probably something like omega q by gh power 3 by 4, right? So either you can write head as gh, or you can also write the head as, how else you can write the head? So this is speed, and this is flow rate, so q dot divided by, instead of gh, what you can write, you can also write it as the pressure by rho power 3 by 4. Both are interchangeable. Okay, so this is what we need to find out. So we already have mass flow rate, so from there you can find the volume flow rate, right? And we can also find delta P, which we also know. Delta P is delta P across pump, so basically P out minus P in. And density is also given. Volume flow rate we can get it from mass flow rate, and only thing is you need to find omega, right? And what is given is, it is given in 30,000 rpm. We need to convert that into the angular velocity. How do we do that?
So 2 pi n by 60 will do.
Wonderful. So it's going to be simply 2 pi n by 60. So it's going to be 2 pi into 30,000 rpm divided by 60. This will give us omega. And volume flow rate, as I said, we can find it from mass flow rate, which is nothing but mass flow rate of hydrogen divided by density. So how much is the density of hydrogen? 70. This will give us volume flow rate, and then delta P is pressure difference across the pump, which is going to be P out minus P in, which is going to be 10 megapascal minus 0.05 megapascal. Okay, so can you guys give me the answer for this?
So omega is 3141.59.
3141.59, okay, radians per second.
Yes, sir.
And this is 10 by 70 is going to be 1 by 7. I do not have a calculator with me. Let's see.
0.1429.
0.1429. All right. That is going to be in meter cube per second, right? And this is going to be 9.95, is it? 9.95 megapascals. So now let's substitute everything together. NS is going to be, so 3141.59 into square root of 0.1429 divided by 9.95, which is in megapascal, so we may need to convert that into pascals, and density is 70, I think 70 kg per meter cube, right? Yeah. So this is going to be your specific speed. How much is this coming out to be?
Reach point 161.
1 minute. There is some. Could you repeat, Tanisha? 8 point? Was it 8?
0.161.
161. Okay. So does that have unit? Oh, we missed the power in denominator. All right, thank you. It's going to be 3 by 4. Sorry about that. So, Tanisha, did you include that?
Sir, I calculate with power.
Okay. So, what is the specific speed then?
It is dimensionless.
Yeah, unit is dimensionless, but 0.161 is right. Did you include 3 by 4 also?
Yes, sir, I
Okay.
consider the power theory.
Okay. Thanks, Tanisha. So this is so yeah, as Tanisha said, this is dimensionless. Okay, so there is something dimensionless is coming. Then it's time for me to ask questions. What is this specific speed? So we use some formula and we found something. What is the use of it? Why we need to find the specific speed? And we are again going to. So then second question is to find speed of operation for increased flow rate. So basically they are asking the speed. N for m dot dash of H2, which is 12 kg per second. How do we find this n? They are not asking specific speed in the second question. They are asking the speed of operation, which means what is the rate at which the impeller is rotating. Basically, rotation speed, RPM. So, how do we find that? So, what this specific speed has to do with that? Anyone want to take a guess?
what is given as 30,000 RPM is the same what we are going to find out. It's already given.
So
Speed for
actually whatever is given was for 10 kgs per second. Now the flow rate has increased to 12 kg per
okay,
second.
okay. If it is increased, then what it is?
So now we are trying to find out speed for the increased flow rate. So okay, so if you guys don't want to answer specific speed, tell me how to solve this second question at least. Both are actually interlinked. Specific speed remains same for a pump actually. Okay, Pranav is telling specific speed remains same for a pump. So we can plug in the specific speed and find m dot. Okay, we can. So Pranav is telling specific speed is same. So why the specific speed has to remain same? For increased flow rate too. Then we need to know what is specific speed, right? So actually, if I want to say, if I want to quickly give you an idea what is specific speed, uh, so that is nothing but a characteristic of a pump. If you select a pump, the specific speed of that pump is going to come with it. Okay, so uh, so it is a as it turns out to be, it's a non-dimensional number. It gives us a characteristic of the pump. Uh, and also it also tells whether to which pump to select. For example, if the specific speed is high, whether you want to go with a radial flow pump or a axial flow pump. So there are different kinds of pump based on your requirements. Based on your requirements, you can select a pump, and that is going to be the selection parameter will be basically specific speed. And also, for example, if you look at this equation here, you can look at this equation. So let's say, for example, if you increase the head, okay, then it's like you are trying to pump the fluid from a low head to higher head, but now so initially it was at h1, now you have increased it to h2. Then what happens with the same pump? If you want to do, either your volume flow rate has to reduce. That is how it has to operate. So basically it kind of links three parameters together, making it actually simplifies the operation basically. So that is where this specific speed is being used. So it also used to select which operation we are planning to do. Based on that, we will try to modify our operating parameters. And also you should note that the volume flow rate you find here is actually the best efficient, or what do you call it? There is some point called best efficient point, something like that, BEP. Okay, so at this efficient point, whatever volume flow rate is what this gives. So let's say for a given volume flow rate you are and for a given pump which decides the specific speed, if you select like I can perform this much delta P, you may not be able to do it because your pump may not be fully efficient. So this volume flow rate you get is for the best efficient point. Okay, so these are few things you may need to consider upon choosing a pump and also choosing its operating conditions. So that is where this specific speed is actually used. And here also, if you look at it, we don't want to change the pump dimensions, we don't want to change pressure gradient, we just want to increase the flow rate. If we want to increase the flow rate with the same pump, so only parameter which is not changing is the geometry. Okay, the geometry of the pump does not change. When you perform a geometric similarity analysis, it turns out that specific speed of this pump will not change depending on the operation, because the pump has same geometry. Okay, so if you are more interested in this, you can look into certain turbo machinery books turbines and pumps. So basically we are trying to achieve a geometric similarity in terms of operation. In terms of same pump is able to do different operations, it is able to work in different operating conditions. Okay, so that's what we are doing. Since the pump is fixed, the specific speed is also fixed. Okay, and we are just trying to increase the flow rate, and because of this increase in flow rate, what are the other parameter getting affected is what we are going to see. And it turns out that, as the question asks, with the RPM is going to get affected. Okay, so I hope it gives you some clarity. Okay, so let's
No,
say
I
this.
just want little more clarification on this.
Okay.
You see, in the specific speed, there
Mm-hmm.
are three factors:
Right.
omega, volumetric flow rate,
Right.
and head or delta P.
Correct.
If we want to, if there has to be the same specific speed,
Hmm.
uh, where are we going to do change? Let's say the mass flow rate has to be different, no, from 10 to 12 kg per second. Are we going to do this change only by changing the delta P across the pump, or are we going to, because that will also involve a different Q.
Correct. 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 True. So
So are we going to keep these constants?
So basically, for a head, for a given head, so it depends upon what is our desired conditions. We may need to pump the fluid for with a certain head, right? So that head would be remain constant. Only thing is, I may need to increase the flow rate. So if I want to keep the head constant and increase the flow rate, if I want to fill the tank a little faster, then what is the thing which I want to change is only omega. Because for a
That
pump,
has to be assumed. That has to be assumed that I like to keep delta P
true,
constant,
yeah, you have to
and
assume that, true.
the change in Q dot will cause some change in omega. So
Huh,
that is going to decide the change in speed.
exactly, true.
Okay.
That is what
But
we
is it
want to
given
do.
in the question? Is it given in the question that we can afford to keep the height same?
It is given in the question that supply and exit pressure needs to be same. So without changing the dimension of the pump,
Okay.
and supply
Okay.
and
Okay.
exit pressure needs to be same. So this one condition will give us geometric similarity without changing the dimension of the pump, which means specific speed will remain constant. And in addition, we are having another assumption that head is same, supply and exit pressure. All right. So this is for operating condition 1, let's say. This is for operating condition 2. So for condition 1, we already found the specific speed. For condition 2, let's say we put omega 2, square root of q dot 2 divided by delta p by rho, and this is also at 2, 3 by 4. So only thing is, this delta p2 by rho is same as delta p2 by delta p1 by rho, which means the same head. And q dot 2 is going to be m dot dash of h2 divided by rho, which is nothing but 12 by 70. So this will give us omega 2. Let me rearrange it. 0.161 into delta p2 by rho, sorry about that, delta p2 by rho is p1 by rho, which is 9.95 into 10 power 6 by 70, divided by power 3 by 4. Okay, sorry, divided by square root of q dot, which is 12 by 70. So this will give us omega 2, and once you find omega 2, you can find n2 also.
So I I directly got N2 as 29773.
29773 RPM. All right. So, okay, wonderful. So you can see that from 30,000 it has reduced to 29,773. So you can see that from here. So since ns has to remain same and denominator is already same, if you increase the q, the w has to, omega has to reduce. So if omega reduces, then n also reduces. So that is what we see. From 30,000 it has reduced to 29,000, which means
Sorry, there's just a small correction. Uh,
mm-hmm.
27179. Sorry,
27179.
27179. I accidentally considered the
27179.
old mass flow rate.
Oh, okay, no problem. So yeah, so around like 27,200 RPMs. Basically, this has to be less than 30,000 RPM. That is what it gives us. Okay. So this will. So this is how we find the speed of operation for increased flow rate. Now we need to find net positive suction rate. All right. What is this net positive suction head? So you guys know the formulas. So I'm not going to ask the formula. I'm going to directly write the formula. So this is what we call it as net positive suction head. And why we need to worry about this parameter? So for your reference, this is at the entry of the pump. This is vapor pressure. Okay. So I guess vapor pressure is also given, which is around 0.006 megapascal, and entry of a pump is 0.05 megapascals. So you can just simply substitute here. Into 10 power 6 divided by density into 9.81. So this will give us net positive suction head. So basically, as the name suggests, it's a suction head, right? If the, let's say your suction head is greater than this, then what happens? The cavitation happens. So the propellant will start boiling, and that's the reason we want to avoid it. Okay, and that's the reason we also find this parameter. How much is this coming out to be? Positive suction head?
Will it be in terms of meters?
Yeah, yeah, it will be in terms
Head
of meters.
meters.
So basically, it's like a pressure difference, but we are measuring in terms of head, right? So basically, the same thing we do it in pumps.
64.139.
4.139
No,
meters.
64.
64.
64.139.
64.074, yeah.
64.1.
75.
Okay.
Okay.
64.075.
Okay.
Okay. The same one. Yes.
64.075. Anyway, it's around 64
Approx
meters.
64.
True.
Yes, sir.
All right. So basically you need to take care of this. It needs to be as high as possible in order to avoid cavitation. That's why you should be little careful with NPSH. Okay, so this marks the completion of this problem. Let's go ahead and solve another problem. By the way, anyone have any questions regarding the problem we solved? I hope it's straightforward and just involves formulas, but a little bit thinking. All right. So if there are no questions, let's go forward and solve this monopropellant rocket. So here we have a monopropellant rocket. It is usually used in satellite correction mechanism, attitude correction mechanism, or altitude correction mechanisms, for example. So there we no need to carry complex engines, for example. You no need to carry oxidizer and fuel. You no need to have a pump. You need to mix it together, and you no need to have that complicated systems. You just need to produce smaller thrust. Okay, so since you need only smaller thrust, bits and pieces of thrust, you can easily do it using the monopropellant rocket. Okay, so uh, in this question what we have is the monopropellant here is going to be hydrazine. Okay, and it is going to generate thrust of 25 newtons over a period of 60 seconds. So basically the rocket is actually designed for only 25 newton thrust, and this 25 newton is over a period of 60 seconds it's going to give maximum. Okay, which doesn't mean like it will start 60 seconds, it will continue its operation and then it will be dead. It won't be like that. So since it's installed with the satellite, whenever there is a correction, it will switch on like 1 or 2 seconds and switch it off. Okay, so that is how they perform this course correction uh, mechanism. So anyway, the specific impulse is also given. The chamber pressure is also given. You can see it's a very low chamber pressure. The hydrogen is injected through 4 straight cylindrical holes in an injector of diameter is also given. The density of hydrogen is also given. And in addition, they have this bed loading catalyst. Okay, so we'll come to that, why we need catalyst, and determine the following. So we are asked to determine certain things. One is total impulse generated, mass flow rate of hydrogen, injector pressure drop, minimum pressure required in the tank, and minimum volume of the tank. What is the amount of hydrogen you are going to take? Okay, and the area of the catalyst bed. So basically you are trying to design the monopropellant rocket for 25 newton thrust over a period of 60 seconds. Okay, so let me write down the given so that it is clear for everyone. So we have hydrazine as our propellant, and the thrust is going to be the thrust is 25 newtons, and specific impulse is also given 1250 newton second per kg. You can also write it in terms of meters per second, both are same. Now the chamber pressure is 1 megapascal, and you have 4 injectors, and injector diameter is given 0.5 mm, and density of hydrogen is 1000 kg per meter cube. And then we have something called bed loading. We'll discuss that sooner. 50 meters per second. So let me try to draw, let's say, a monopropellant rocket. So you have this combustion chamber, and then you have this nozzle. Okay, and then what do you have is you have something called catalyst bed here. and then you have like four injector for hydrogen. So it enters here. You have pressure here to be 1 megapascals. It's a combustion chamber pressure, and hydrogen enters through this injector. Okay, and what else is given? Yeah, that's it. Yeah. So, why do we have a catalyst bed here? This is a question you should ask me. What is the reason to have a catalyst bed?
This is to initiate combustion, otherwise
True.
monopropellant will not burn to
Huh.
activate it.
Correct, correct. So yeah, it is basically to initiate combustion, but in addition to it, what it also does is hydrogen is a monopropellant. So uh, actually, it has to, yeah. So it has to decompose, and then it has to react, and then generate products. So that is the reason we have a catalyst. It will make this process a little faster. We do not want a slower reaction to happen. uh, that's why we have this catalyst bed, and this bed is actually a porous bed through which hydrogen flows, and then it also reacts, and then gases gets generated, and as Ram sir told, it's going to this is just to increase your reactivity of your monopropellant. Okay, so that it will once it comes out, the temperatures here will be very high, and so you will get larger thrust here. That's the basic reason we are interested in catalyst bed. So basically we were asked to find what we were asked to find. Let me also write down that. So we were asked to find the impulse, which is straightforward from rocket propulsion 101 from first class. You know how to find. And then we were asked to find the m dot of the hydrogen, and then we have injector pressure drop, delta P of the injector, and then we need to find minimum pressure required in the tank. So here I didn't draw a tank, I just draw the combustion chamber, so we need to draw a tank. And then also we are asked to find what is the volume of the tank. Okay, and then you have area of the catalyst bed. So what is this area of the bed? What is going to be your area of the combustion chamber, or cross sectional area of the combustion chamber? Okay, all right. So if the question is clear for everyone, maybe we can go ahead and solve the problem. First is to find impulse, and how do we find impulse?
Sir, what is bed?
Bed, you mean? So this whole thing we call it a bed, basically. Is that your question, Tanisha? Tanisha, for some reason I'm not able to hear you. Probably my hello. I think there is a problem from my side. Hello.
Yes, sir.
Okay. So am I
You're
audible
audible.
now? Okay.
Yeah, you are audible. You
Yes,
can
yes.
continue speaking.
Okay. Okay.
Only,
Okay. Thank you.
some question raised by Tanisha is not clear, but your voice is audible.
Okay. 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 Thank you. I thought there is some problem from my side. Anyway, so the catalyst bed is nothing but there is some porous, you know, kind of plug which is kept inside the combustion chamber. We just name it as a bed. That's it. It's like kind of this mesh present here. Okay. So 1 minute. I think there is some problem from my iPad. Let me rejoin. All right. Okay. Sorry about that. So Uh, so first is we need to find impulse. How do we find impulse from the given data? So I think I missed one of the data given, which is 25 Newton for a time duration of 60 seconds. Okay. So we need to find impulse. So we have to either use the specific impulse formula, or we need to use the thrust formula, right? So burn duration is also given. How do we find impulse?
Yeah. Just multiplied by time.
Impulse multiplied by time. Okay. It's nothing but is equal to force, right? So if that is the case, you can write F by T. So impulse is nothing but change of momentum, right? And force is nothing but rate of change of momentum. So what is the impulse?
So actually, it's the other way around.
Okay. I heard someone saying that's what.
Impulse is force into time,
Okay, force into time.
and
It's not impulse times time. Okay, very good. So
Yeah, it's force into time.
yes, sir.
so it's going to be
And
25 into 60, is it?
well, impulse is basically, sir, the sudden change in momentum that occurs due to
Correct.
application of force.
Correct, correct. So impulse is nothing but change of
Since
momentum.
force is
Force
rate
is
of change
nothing.
of momentum, yeah,
Exactly. Force is
rate of change of
exactly.
momentum. So multiplying it by time will give us the impulse.
So that's why we write force is nothing but impulse by time. So change of momentum by time will give us rate of change of momentum. Okay. So how much is the impulse coming out to be?
1500, 1500.
1500 Newton second. Okay. Now, what is m dot? That you can find from specific impulse, I guess. ISP is
So it's force upon mass flow rate. So
okay.
mass flow
Wonderful,
rate will be force upon specific impulse.
wonderful. All right. So force is 25 newtons
That is
and
coming out as 0.02.
0.02.
0.02. Okay.
02 kg per second.
Okay. 0.02 kg per second. All right. And
So now we multiply.
uh, could you repeat, Pranav? So now we need to find delta P of injector, right? How do we find out? We already know a formula. We discussed a lot of times in the last class. So mass flow rate through an injector is nothing but CD. What else was there? A, area of injector, square root of 2 times, I guess, delta P of injector by rho. Is it? I'm very bad in remembering formulas. So is that fine? So if it is fine, we need to find delta P of injector. For that, we need to know what is the mass flow rate through an injector. What is mass flow rate through injector?
We can divide it by 4, the total mass flow rate.
Wonderful. So it's going to be simply 0.02 divided by 4, which is 0.005 kg per second.
Now, in this formula, you have to multiply it with the density also.
Yes, sir.
So
It's,
this is area into velocity multiplied by density to get the mass flow. Yes.
yes.
Wonderful.
So eventually it will come within the square root multiplying with the delta p term
Wonderful.
within the square root. Anyway,
True, true. Yeah, right. So, but we don't know CD, right? CD is not given in the question. So, for this, maybe I will take CD to be 0.96. Okay, maybe. So, if I include that here, 0.005 is equal to density of the hydrogen. Is it given? It's 1000. Okay, so 1000 into 0.96 into area of the injector. Area of injector, we know the diameter of the injector, it's 0.5 mm. So we can write the area of injector to be pi by 4 into 0.5 mm, 0.5 into 10 power minus 3 whole square into square root of 2 into delta P is what we are finding out, divided by 1000. Okay, so how much is this coming out to be? Let me just rearrange for the sake of completeness.
So pi by 4 may not be
The
inside.
bracket,
will not be inside the
in the
square thing, bag of water.
Oh,
permeable
sorry,
going
sorry.
outside, right?
Sorry.
Diameter squared.
True, true. Sorry.
Yes, sir. Yes.
So, how much is the pressure coming out to me? I mean, pressure gradient.
So can you simply find the pressure through the pore and subtract it from the chamber pressure?
Sorry, Tanisha, I couldn't fully hear you. Could you repeat once?
So first we will find the pressure through the pore injectors by force per unit with the help of diameter which we have provided, and then subtract it from the chamber pressure to find the delta P.
Well, basically, we don't, we directly find the delta P. So here the delta P is through the injector only. Okay. So, okay, let me draw it so that we no need to find separate pressure. Actually, we cannot find pressure from this equation. We can only find the delta P from this equation. Okay. So let me try to draw. Let's say if this is P1 and this is P2, this is the whole injector I'm talking about. Basically, from this equation, the delta P injector is nothing but P1 minus P2. Okay. You can find only P1 minus P2. The real pressure you need to find out only after finding the or only after we know the chamber pressure. Okay. So the delta P we find here is going to be directly the delta P across the injector. Is that, isn't that what asked in the question? So we are asked to find the injector pressure drop. So basically the delta P. Okay. Was that your question, Tanisha? So we do not find separate pressure. We directly find the pressure drop only from the from the formula. I hope it's clear for Tanisha. So how much is the delta P you guys want to know?
by this much amount.
All right. Thank you. I'm back. So as Ram sir told, were you guys able to find out the next question also? So it's around 0.315. I heard 0.315 megapascal is the pressure.
Point 0.35
Okay,
megapascal.
351. Sorry about that. 0.351.
0.35 megapascals is the delta P. So that means the injector pressure has to be 1.35
Wonderful. Yeah,
megapascal.
true. So the next one is to find in pressure in the tank. So pressure in the tank should be chamber pressure plus some delta P of injector. So it's going to be 1.35 megapascal. That is true. So now we need to find volume of the tank. How do we find volume of the tank? So what would be the logic to find volume of the tank? So this is the tank and we have pressure in the tank to be 1.35 megapascal, which is going to be filled with hydrogen, and hence and then you
How do
have
we
to,
find the, how did we find the tank pressure? 1.35?
the one we found 1.35 will be the tank pressure, right? So the tank is directly connected to the injector. I'm sorry, I didn't ask you guys that. So tank is
Okay,
connected to the
okay.
injector. Tank and the combustion chamber is connected together, right? So this is the
Okay, there is
combustion
no
chamber.
pump here.
We don't need pump.
There's no.
Yeah, there is no pump actually. So it's also not given in the question that there is a pump. And usually monopropellant rocket will not have pumps basically. So the pressure in the chamber is 1 megapascal and pressure in the tank is 1.35 megapascal, and 0.35 megapascal is lost due to the injector. So now we need to find volume of the tank. So what is the total volume of the tank we require? And one clue is
I
we have
think
to,
we have m dot. We can find mass and we have density, so we can find volume.
exactly. So we have m dot, rate at which we are the total m dot we have. This is the, and also we also have the burn duration 60 seconds. So we know
Yes,
how
so the
much
total
exactly the
volume we will
mass.
be able to find.
Uh, could you repeat? Kileshwar?
Uh, uh, we will be able to find the volumetric flow rate using density divided by density,
We can find volumetric flow rate, but we
and then
also have
multiply it by the time.
time. Yeah, that is also true. You can either find mass of the hydrogen, total mass of hydrogen we require for 60-second duration, and then you can find the volume of the tank, or you can directly find the volumetric flow rate, then you can find volume of the tank. So m dot into t. So basically the idea is we need to have that much hydrogen in our tank. That's why it's called minimum volume of the tank. So this will give us 0.2 into
So
6,
1.2
1.2 kg per
1.2
second.
kg divided by 1000, so it will be
Sir, just kg.
Sorry.
so only kg. Only kg.
Hmm.
And
And then
divide this by the density, so it will be 0.001.
That means it's coming in terms of centimeter cube.
right, it will be.
This is very low value. 1.2 into 10 to the power minus 3 is a meter cube.
Hmm. So it will be 1.2 into 10 power minus 3 meter cube. We can also write it in terms of liters, right? So basically this is the volume of the tank, and finally we were asked to find the area of the bed. Okay.
So what do we write then? 1200 cc centimeter cube?
We, it's up to us. So you can also write it in
So
terms of liters.
so as far as I know, it will be basically 1.2 liters exactly.
So you can
If we
either write
convert
1.2
Yeah.
liters or
1 meter cube is actually 1,000 liters. So it will 1.2 liters. Will be so.
Okay.
so area of the bed is going to be
Mass flow rate by the catalyst. That value
right.
I forgot.
So it's
Bed
the
load
bed
catalyst.
loading ratio. So the bed loading ratio is
Into
actually
one time also. Into
so
one time also, I guess.
one
You just
point
have to convert the mass flow rate into gram per second.
exactly. So it's in 1
Yeah.
grams per centimeter square second. So either you convert gram and centimeter to meters, or so we can find the bed in terms of centimeters. So maybe we can convert m dot in terms of gram. So you can write 10 power 3 divided by BL is 1.
It's
One.
So gram per centimeter
20.
square second. This is gram per second. So the area of bed is going to be 0.02 into 10 power 3 centimeter square. That's it, right? So basically bed loading ratio is actually defined as mass flow rate per unit area of the bed. So uh, we can use that definition to find out this, or this can also be written as 20 centimeter square. Okay, so is that clear? How do we do this problem? So only thing is we need to understand how this thing is happening, how the operation of monopropellant rocket is happening. There's going to be tank. There is no pumps. Uh, there will be injectors and there will be a catalyst bed. That's it. Any questions regarding this problem? All right. So I hope there are no questions. So what I thought was I will revisit this problem again, and then I will. There's been a lot of confusion, so I thought I will explain with a different way. So basically in this question we were asked to find the initial surface SBI, basically these surfaces, initial burning surface, and also the maximum burning surfaces SB max, right? These are the two questions we were asked to find. SBI will be straightforward, you can find it, but SB max, if you know how to find it, then the same logic you can apply to find the volume of the sliver. Okay, the SB max and volume of the sliver is actually related with each other. Okay, so let me try to draw it in a in one 1/4 of this. So so in this what we have is we have, let me draw, let's say, initial uh, propellant grain. So it will look something like this. Okay, and let me draw it something like this. So three boxes from here. Okay, So this will be our one half of the propellant grain. So sorry, one quarter of this. So basically one quarter of this propellant grain I'm drawing, and just multiply by 4 will give you any parameter we are interested in. So here the question would be what would be the let's first try to find out. So this is the propellant grain. So the initial burning surface is going to be, so if I want to draw this, it's going to be, this is going to be b by 2, and this is also going to be b by 2. Okay, and this whole thing is going to be d by 2 is the outer grain diameter. Okay, now what we have is we have number of points here. So these are the uh, so these red points, in addition to these lines, is going to regress. Okay, that much we all know. So this is our initial surface area. So if I want to calculate it, so for example it is going to be 4 times uh, this line length, which is going to be b by 2, and this is also going to be b by 2. So it's going to be b by 2 plus b by 2 into the length, so which is going to be in the z direction. Okay, this length, and that is what we write it as 4 times b l. So this is straightforward, this everyone knows. Now the question is, what would be the maximum burning surface area, then when that will occur. So once the maximum burning surface area occurs, then whatever the burning is going to happen, that is going to be a sliver burning. Okay, and the maximum burning surface area corresponds to the end of the web burning. Okay, so when that is going to happen is the question. So for example, let's say if we slowly regress these surfaces. Okay, so now there is no delay. So now let's say we have this surface. Okay, let me mark it some name. Okay, so a, b and c. Okay, now a, b surface is going to regress. Let's say after certain time it regresses to a new value somewhere here, this green line. Okay, okay, so this ab regresses to this line, so this a point regresses, and since this is a line, this is going to regress with the it's going to regress straightly. Okay, now similarly the bc line will also regress one cell. Okay, similarly. Now the question is, what is going to happen here is the question. So if you are able to find out this correctly, then everything would be right. So now how this is going to happen is, since this is a point, okay, this b is a point, it is going to regress in this direction, and all the line sources is going to regress as a spherical surfaces. Okay, so this is the point source, or in terms of with 3 in 3D direction, it is a line source, and line source is going to regress in a spherical uh, manner. So there is going to be spherical surface like this. Okay, I think there is a delay. Okay, so uh, till here is this clear? So we have this spherical surface. Now we need to find out what is the spherical surface, how, what is the radius of the spherical surface. Okay, that is the main question. So this spherical surface, if you want to find out its radius, you have to measure it from this point, from point B. Okay, because from there only it started regressing, so you have to measure it from here. So now we have regressed like one cell. Okay, in terms of in this graph, let's say we have regressed one line. Okay, from this line we went to this line. So whatever the distance of this, let's say some delta, that will be the radius of this, and that has to be measured from B. Okay, this is going to be the radius and that has to be measured from B, and this curvature no need to exactly coincide with the outer diameter. Okay, this curvature no need to exactly coincide, or this curvature, let's say if you extend, it's going to become a circle here. It will not be concentric with the outer. Okay,
I see.
the reason is it has
Since
started
its
from a
radius
line
is
source.
less,
uh, yes, Akhilesh?
its radius is less, so its curvature will be more than the outer one. So it will
Exactly.
not
So yeah,
coincide with it.
exactly.
It will
So
be
the
within
reason
it.
is it started from a point source or line source. It is a corner, and from here the burning started. So whatever happens, whatever the radius you are going to measure, it's going to be from this point, and that's how you get this curvature. Now let's say if we continue, and if you regress for some more distance, let's say you regress it to the next level. Okay, you will regress it till here. Okay, if you follow this purple line, and then you have this curvature. It's not exact. Wait. Again, this may coincide with the outer or it may not. Okay, and the so let me draw this radius also. This is some radius which is measured from B, and this is some other radius which is again measured from B. Okay, and this may coincide or may not coincide. At this point it looks like it coincides. So as soon as it coincides, what happens, you will have a maximum burning area there, because after that there is no way this curved surface can regress, because it has already reached the outer surface area. Okay, so this basically the radius here and the radius here is going to be different, and hence while you calculate you should take care of this radius properly. Okay, so if this is the case, then whatever left is actually the sliver. Whatever left here is actually the sliver. Okay, so again, if this is the case, let's try to find out the maximum burning surface area, and this purple line, let's say we call it delta max, and this is nothing but the web thickness. So this is the minimum distance. This is a minimum distance from the inner surface to the outer surface in the initial burning, right? This is the delta max. This is the web thickness that we already know. So when this reaches the web thickness, that will be the radius for this curved surface. Okay, and if that is the case, you can similarly find the maximum surface area. And how will you find the maximum surface area? Again, you can, this is going to be b by 2. Okay, and this is also going to be b by 2. These two is not going to change, and then this is going to be a quadrant of a full circle. Okay, so let's try to add all these. B by 2 plus b by 2, and quadrant of a full circle, and that circle is nothing but this is the circle, right? And in this circle we are just taking a quadrant, the perimeter of the quadrant, and that is going to be pi by 2 times delta max, because we are just taking quadrant, which is 90 times delta max, and this whole thing multiplied by L in the z direction. So this is going to be your SB max, and if you know the SB max, then you know the perimeter. Similarly, you can find the area also. you can find the whole area, and then you can subtract it the remaining area. So let's try to find the sliver mass. So sliver mass will be, again let's say, so volume of the sliver. Okay, once you find volume of the sliver, you can find the sliver mass. Again it's going to be 4 times this whole circle divided by 4 is nothing but pi by 4 divided by 4, pi by 16 into d square, minus this whole circle minus these areas, right? I think there is a delay. Second. So minus this shaded area, 4 times the shaded area is going to give you this sliver mass, okay, or sliver volume. So how do we find that? Similarly, we can take this as a uh, we can take this as a separate box, this as a separate box, and then this as a quadrant, again area of the circle divided by 4. Okay, so this is going to be b by 2, and how much it has regress, it's going to be delta max. So there is two squares, which is uh, b by 2 times b by 2 plus 2 squares into b by 2 into delta max, right? So there is this square b by 2, and then you have this square and this square, both are b by 2 times delta max, so that's why I wrote it twice. Okay, and then you have the area of quadrant. Area of quadrant would be uh, pi r square divided by 4. So pi by 4 delta max square. Okay, this whole thing multiplied by length of the grain. So this is how you get volume of sliver and also SB max. So coming to Ramsar's question, so let me draw it once more. So is this
No,
clear?
I realized I was wrong. I was wrong.
Okay, okay.
This is
So
the correct approach.
right, right. So basically, what you did is not completely wrong. Only thing is you try to measure this radius from the center. So that is why you were
Yes.
having, a little, your curvature is same as the curvature of the outer diameter, and that is why you reach the final smaller line, smaller
Yeah.
volume. But
That is a mistake. I realized the mistake.
right, right. Okay. I I'm glad you were able to understand. So
This is correct. This is
okay.
correct.
So this is basically, I think, the formula given uh, in the solution also. So if you simplify this, you will end up having the formula given in the solutions. Okay. So were everyone able to understand? I think last time there was one more student also, Muhammad Ijlal, also asked the same question.
It's clear, sir, now.
All right. Thank you. So any other questions you have? Same thing.
No, sir.
Okay. So that is what I have today. I have these two questions. So if there are any questions you have, you can stay back and ask. And if not, we will meet next week. I think we have two more interaction sessions. I hope there will be one more also for a revision. So probably we'll be meeting 3 more times for this course. All right, guys. Thank you. There are no questions.
Alright,
Or
sir.
if you have, you can stay back. I will be here for another.
Okay, thank you. Thank you. No questions. No questions.
Thank you very
Thank
much.
you.
Thanks, Ramsar. Thanks, Akhileshwar. Thanks,
Uh,
Pranav.
Thank you, sir. Sir, in the last, we'll be having, you said we'll be having a revision lecture in the last, like,
Right,
so
right.
we'll be revising all the concepts from like lecture one, like so.
Yeah, yeah, sure. Yeah, we'll be doing that.
Okay, okay, okay.
So that will probably be on April 18th, basically. So,
Okay.
so I think it might be on Thursday sometime. Where is the calendar here?
So, okay. So why so, sir? Means why not on Saturday?
I'm not sure. So basically, I think there is a. I have been told that last day could be maximum could be Thursday only. Yeah. So April 18th only. So after that, I think there might be some. You guys also have exams, I guess, in the next week, coming week.
So it's
So
on 27th, I guess, the exam.
I see.
There's just one exam, I think, on 27th April,
Okay.
Saturday. I think.
Okay.
Yes, sir.
I'm not sure why they said, but they said last class could be on maximum on April 18th only. So that's why it's scheduled on last day, April 18th. So it will be again on same timing, I guess, April 18 from 7 to 9, Thursday. Okay.
Yes, sir. But if possible, if it can be on Saturday, it will be better since
I see. I will, let's say I will, I will ask them. I will ask NPTEL. Let's see what happens.
On the
sure, sir.
website, it's saying that the course end date is 12th April. So I think they're like compensating for that
I think that is the,
one.
I think, yeah, yeah. That could be the reason. Anyway, I will see what I can do. I will try to ask them. Or else if you guys want, we can also meet on 20th. It may be unofficial also. If you want, we can meet on 20th. We will anyway conduct one on April 18th, and if you guys want, we can meet on April 20th also. No problem.
Actually, it would be better if it is not a weekday, because you
Yes,
guys
sir.
have
Exactly.
classes.
No problem.
Yes.
No problem. We can meet on 20 also. I will be available. Even if it is not official, we can meet on 20th. It's fine.
Okay.
20th should be Saturday, right? Anyway, I have
Yes,
scheduled
sir.
it.
Saturday.
Yes.
Anyway, I have scheduled it. We can meet on 20th. No problem.
Okay, sir.
Okay, okay. Thank you.
Thank you very much, sir.
Thanks, Manu. Thanks, Akhilesh. Tanisha, I'm not able to hear you. Were you able to understand the catalyst bit? You were asking something, and also the injector pressure.
Yes, sir, I understood.
Okay, okay, all right.